Magnetism of isolated running charged particles. Magnetism is not always uniform and continuous. The magnetic flux density B can only be applied inside a solenoid coil where a group of charged particles is in uniform motion. Running charged particle has the magnetic effect that decreases spherically around it. The magnetic effect that is provided by charged particles running in a vertical row decreases cylindrically in horizontal direction. Charged particles running in parallel pull each other, and when they run in opposite directions, they repel each other. Fig. 1 shows an understanding of the direction of the force acting between magnets by using representative of moving charged particles. Understanding of magnetism on Meissner effect by the behavior of superconducting charged particles. The superconductor levitates upper on a permanent magnet. This Meissner effect can be explained by the motion of superconducting charged particles induced by the magnetic field of the permanent magnet. According to Lenz's law, when a bar magnet is brought close to the coil from the axial direction, an induced current flows through the coil, and the magnetic field is in a direction that prevents the bar magnet from approaching. Similarly, in a superconductor, a rotational motion is induced in superconducting charged particles, which are currents that shield the external magnetic field, resulting in the Meissner effect. A Karanov-Bohm effect shows a microscopic magnetic reaction between motioning charged particles. A Karanov-Bohm effect is related to the phase of the wave function of quantum mechanics. As shown in Fig. 3, when an electron beam is divided and passed through the upper and lower sides of the outside of the solenoid, interference fringes appear. The appearance of interference fringes can be explained by the fact that the amount of change in the angle of rotation due to torque becomes the amount of work of the rotational motion. With respect to the motion of charged particles flowing through a solenoid, for the direction of motion of electron beam passing through the solenoid differs between the upper and lower sides of the solenoid. Electrons in a beam passing in the same direction will pass through the low energy region, and electrons passing in the opposite direction will pass through the high energy region. This effect was demonstrated in 1986 by Akira Tonomura in an experiment with a sample covered with a superconductor solenoid. The phases of the wave function are repeated in 360 degrees, and the characteristics of the phase difference can be discussed in parallel or anti-parallel. Now consider the mechanism of magnetism. The torque Fb received by a charged particle q passing through at velocity v at the magnetic flux density B is given by equation 1 according to the Biot-Savart law. The amount of angular change in torque Fb received by the action of magnetism is the angular change in the rotational energy um. Here, the negative sign in equation 2 is set to be lower when v and a are parallel. In equilibrium, this magnetic energy balances with the repulsive energy of Coulomb and does not coalesce. In general, the torque is given by the rotation operation of the vector analysis of the rotational energy. Therefore, if the vector potential A, which gives rotational energy to a charged particle in motion, is defined by equation 4, the torque is obtained by equation 5. Rotation A means that components of orbital direction are added in the circle gives the magnetic flux phi, which is the total amount of B here. Vector potential A decreases as it moves away from charged particles. The change in the rotation angle of a result that rotation is applied to the charged particles entering the field. In this way, the action of charged particles moving individually is due to the rotational energy that decays with the square of the distance, so it cannot be handled by a uniform B. As shown in Figure 4, a localized magnetic field density B is generated by the motioning of the charged particle q. Magnetic field density B is defined by the rotation of A, which gives the rotational energy of the motioning charged particles. The vector potential A decreases in inverse proportion to the square of the distance away from the charged particle. Behaviors of charged particles in the surface of the Sun. In the photosphere of the Sun, the density of charged particles is high and the temperature is 10,000 K. But in the coronal region, the density lower and the temperature rises to 1 million K in the area from the photosphere to the corona, i.e., 3,000 to 10,000 kilometers. Elongated protrusion structures, so-called spicule, are observed. Since there is a magnetic coupling between charged particles moving in parallel at high speed, charged particles of the same polarity running in parallel form a bundle. The bundled H+ rises and is pulled back to the Sun by gravity to create a protrusion structure. The speed of escaping from the Sun's gravity on the surface of the Sun is 617.5 km per second. The ascended spicule descends due to gravity, but charged particles with a velocity greater than or equal to the escape velocity are ejected from the Sun. The total amount of charged particles H+ emitted is estimated at 1 million tons per second. When H+ running in parallel becomes a large group due to magnetic coupling, it becomes a flare by self-amplification. The huge mass of charged particles does not diffuse. So, it reaches to the Earth. It causes geomagnetic disturbances, so-called magnetic storm. Once a huge magnetic storm had destroyed the North American power network. Distribution of hydrogen atoms upper sky of the Earth. As shown in Figure 0.6, the concentration of hydrogen atoms H in the sky peaks at about 80 km altitude of the Earth. This is an evidence that hydrogen ions of the solar wind continue to invade the Earth. At an altitude of 80 km or less, H+ in the solar wind collide with nitrogen molecules N2 and oxygen molecules O2 on Earth, and H+ becomes to form atom of H or molecules of H2. Since the weight of those materials is light, those are released from the Earth. In the early Earth, the atmosphere was mainly composed of carbon dioxide CO2, so the hydrocarbon molecule CnH2n+2 was synthesized by the collision of H+ in solar wind. Cell membranes of all living organisms are mainly composed of C16H34 or C18H38. These organic molecules are liquid state on the surface of the Earth. Since the specific gravity is less than 1, and hydrophobic, those molecules are gathered on the surface of the water and eventually form the cell membranes of living organisms. Atmospheric motions around a planet driven by the solar wind. The solar wind has angular momentum that rotates counterclockwise due to the rotation of the Sun. The atmosphere near the equator of Venus is moved from east to west by the solar wind, which collides head-on during the day. As shown in Fig. 0.7, the action of the solar wind, which moves the atmosphere from east to west, is weaker on planets farther away from the Sun. On the other hand, in the mid-latitudes of the Earth, the influence of the solar wind, which passes on the east side in the same direction as the rotation of the Earth, acts to flow the atmosphere from west to east. Interaction of H+ of solar wind with the Earth's atmosphere. The Sun not only imparts radiant heat from sunlight, but also H+ with mass collides with the atmosphere. In the mid-latitudes of the Earth, westerly winds blow, but near the equator in the daytime hemisphere, the solar wind collides head-on, as the gears engage and the atmosphere is driven clockwise. Therefore, the atmosphere around the equator in the daytime hemisphere is shifted in the opposite direction to the rotation of the Earth, and the trade winds blow. H+ of the solar wind passing through the eastern side of the Earth magnetically couples with the charged particles of the Earth rotating in the counterclockwise direction. On the other hand, the H+ of the solar wind passing through the western side of the Earth is opposite to the movement of charged particles of the Earth and is magnetically repelled. The Earth as a whole moves its atmosphere from west to east faster than its rotation. So, the weather in the west is moving to the east. Diurnal changes in the geomagnetic field during the geomagnetic quiet day. Magnetism has several factors, each of which has the period of the change. There is magnetic field fluctuates in a daily cycle as shown in Figure 9. The geomagnetic field measured on Guam Island increases by only about 0.1% 50 nanotessera of the geomagnetic field around noon. This phenomenon is clearly observed during the quiet days of the geomagnetic field. This can be explained that when the H+ of the solar wind, which has a rotating component in the counterclockwise rotation direction, is irradiated from the front around noon, it drives charged particles in the sky in the clockwise rotation direction and weakens the geomagnetic field associated with the rotation of the Earth. On the other hand, free electrons generated by ionization of molecules in the upper atmosphere due to irradiation such as ultraviolet rays of sunlight combine with H+, reducing the effect of H+, weakening the geomagnetic field. Since the mass of H+ is 1,836 times larger than that of electrons, the motion of electrons does not affect the motion of the solar wind. Summary. Magnetic phenomena can be explained by the aggregation of the magnetic effects of isolated charged particles in motion. Magnetic phenomena have been explained conventionally by setting the magnetic field first. However, a uniform magnetic field is generated by a group of charged particles that flow uniformly and continuously. The behavior of plasma on the surface of the Sun can be explained by considering the motion of charged particles first, rather than the magnetic field first. The hydrogen ions of the solar wind are invading the Earth, shifting the current Earth's weather from the west to the east. The theory that hydrogen ions in the solar wind are protected by the geomagnetic field as a barrier is incorrect. In the early Earth, hydrogen ions in the solar wind reacted with carbon dioxide in the atmosphere to synthesize hydrocarbons, which played a major role in the birth of life. Thank you for your attention.